The next thing that I want to cover in terms of using libraries correctly is Rayon. And what I want to do is revisit the n-body parallel program that we saw earlier. You might have noticed I said, okay, given the original n-body program, we got a small amount of improvement by using the bins routine, and that it mattered how many points we had, but actually that the benefit to that was quite small in comparison to actually parallelizing it. And I didn't really show you how I parallelized it. We're going to look at the code, but spoiler alert, it uses Rayon, which is a data parallelism library. This library is intended to take what is an existing sequential computation and then turn it into a parallel one. And in an ideal world, if you know in advance that you want to parallelize a thing, then you can absolutely design it from the ground up in such a way, and then you wouldn't maybe want to use this library because there'd be no point, because you have, again, built the parallelism into the original design. That is, of course, not always what happens. Instead, you start out with a program that is initially just pretty serial, and now you want to parallelize it, or you have an algorithm that's already written, or other code, something that didn't start out as parallel, and you're going to make it so. That is totally doable, and I mean, you could do a full major rewrite. However, you don't have to, because of the existence of something like the Rayon library, where you can drop in a relatively small change and end up parallelizing something that would otherwise be serial, and with relatively little effort at that. So, all right. Thinking about our n-body problem, I mean, the hot loop, that's where the majority of the time is going, is the calculation of forces. Unsurprising. We don't have to spend a lot of time opening up a profiler and identifying, oh, where is the time going? It would be in calculating forces. Okay, thanks, Captain Obvious. So, given a vector of points, if there are n points, we know that we could calculate the force on each one independently. We covered that a little bit when we talked about the n-body problem as a concept, and we know that we could do that kind of thing in here. And honestly, my initial approach was don't use a library. It was spawn threads and move things into the thread, and at first glance, the first problem that you would encounter is you can't borrow the accelerations vector as mutable more than once. When you are doing this kind of problem in C, you don't have to really worry about that. You can pass a pointer to the same buffer to every thread, and as long as every thread is good about respecting the rules and making sure that it only edits the part of the vector that other threads are not going to touch, then everything works out just fine, and there's no cause for concern. However, that is not as straightforward in Rust because, well, we can't just assign the vector to one place. I know this operation that I want to do is correct and won't have race conditions because each element in the vector is being modified by one thread and one thread only. But we would still have to be very explicit about how to split it up. So, yeah, even though each element in the vector, I know my code will only modify in one place, Rust doesn't know that, and the compiler erring on the side of caution says, I don't think so, I can't allow this. Now, there is a way to do that. And you can split a vector into mutable chunks using this function split at mute, and you can divide the slice into two pieces. If I want to hand it out to 4 different threads and say, you know what, you get the first quarter and the second thread gets the second quarter and so on, you could do this, and you're just dividing the vector up a little bit as you need. It will get the job done, and if you want to subdivide it more and more until we're down to like having individual elements, maybe what we want is recursion. We could also think about something like making it producer-consumer, where we have the main thread throw items into a queue, and we have multiple consumers taking it out and processing each one and returning a result, but don't reinvent the wheel. I believe in code reuse. Copy-paste approach I've sometimes heard referred to as clipboard-based inheritance, which, I certainly think that's funny. I don't know if that joke would be a smash at parties, but no one's going to parties right now amid a pandemic, are they? I hope not. Anyway, okay. Don't reinvent the wheel. Let's use a library, and we're going to use Rayon for this. Okay, so we'll take a look at the code for the n-body parallel problem. We can also look shortly thereafter at the bins version of it, but if we just take the original and we want to apply Rayon to it, here's what we get. I have to, on line 3 there, include a prelude, which is just a requirement that brings in some traits into scope so that our code works as expected. Fine. And we've already identified that the slow step is computing the interactions. It's reasonably common, I think, that computationally intensive parts of the program happen in a loop. Maybe each individual iteration of the loop isn't super expensive, but we do a lot of iterations of that loop, resulting in a fairly large total cost. And so making a modification to that loop is very profitable in terms of speeding things up. And our hope, of course, is to achieve a good amount of speed up at a very low cost. Cost in this scenario is not necessarily money, but it's programmer time. Programmer time is expensive and is a limited resource, let's say that, if nothing else. And there are costs associated with any change that you want to make, and that somebody has to write the code, test it. You do test your code, right? I mean, please tell me that you do. If you don't, I have questions, but you should. And if you have reviews, code reviews, those take time for other people to review it. And, the bigger the change, the more expensive the review is in terms of people's time and effort. And, of course, more potential that they ask you to change something, and then that has a cost all its own. Where you have to wait for that and rework it and resubmit it and have it built by by continuous integration again, and maybe in the meantime somebody has merged, so you have to rebase and all that. Like there's a cost to any delay in code being approved and put into the production branch, whether you call it the main branch or particular feature branch or something, it doesn't matter. So if we can make the change minimal, that's good. Saves money, saves time. All right, so ultimately we'll go down to body-body interaction and see that actually nothing has changed here. Why? Because the calculation of forces isn't really the part that needs changing. It's how we actually interact with it, how we call it. Where we have the loops that matters. The calculation of forces between any 2 points isn't wrong, isn't itself a problem. It just is where time is going, but the loop is where we want to make our change. And in calculate forces, here at line 61, we've actually got a lot going on, and this is really the difference. So before this, I had a for loop here that was for int I equals 0, blah, blah, blah. In Rust, of course, so it was for I and then the range. And what we're doing instead is we're using the Rayon trait parallel iterator mutable. Okay. Rust usually recommends iterating over a collection with some iterator as opposed to using the for construction, because when you do that, Rust can skip some of the bounds checks because it knows that the iterator won't go out of bounds because the iterator can only operate on elements that are in the collection, and there's no need to sweat about whether index 10 is beyond the end of the array. So that's a little bit helpful on its own. However, what I've said here is that we want a parallel iterator as opposed to the sequential iterator. That's something that makes it very easy to drop in, because a normal call to the iterator, we just replace it with the parallel iterator and we're ready to go. Obviously, we want it to be mutable because we're intending to change the accelerations vector. Instead of iterating over the collection sequentially, the parallel iterator cuts it up into slices of size 1, and I ask for the enumerate option here because I actually care about the loop counter, the loop induction variable. That would be I in this case, because we're going to use that, and we're going to use it here in getting the value from initial positions. And then I provide the operation that I want to perform. And for each says, given that we're iterating over this collection, I want to take a particular action on each thing in there, and that action is for each item, run the code in this block. And then I specify some variable names for things, index name I, and current Excel, the name of the variable I want to use for the element in the collection that we are looking at. Okay, so that is going to then create different little slices of the acceleration vector, hand it out so it can be done in parallel, and then as it is done in parallel, these this block of code runs, and in the end, all the results are gathered, and accelerations vector is up to date, and we're done. Everything has worked. We have accomplished the calculation in, well, quite a lot less time than it would have taken otherwise. And if we run it, we could actually see that even given, how many points do we have here? 100,000 points, it actually is significantly faster than the original n-body program where this was running and we kind of gave up waiting because it took a little bit too long. While we wait for that and can hear the fan spinning up in the laptop, we can also see that that's really the only thing that we've had to change. Initialize position hasn't changed, initialize accelerations has not changed, and main has also not changed. So really our change set is quite small, and I'll show you in a bit exactly how small it is, in a way that is even a little bit surprising. That the change is very, very minimal. We did have to, of course, include Rayon in our cargo configuration, but that's otherwise not too bad. All right, I decided I would just cut short that part of the video because no one wants to watch dead air for a couple of minutes while you can maybe faintly hear some CPU fans in the background. In any case, looking at the parallel version of the n-body bins program, we can see it also is very similar to what we saw earlier with the n-body bins, in that really the only thing that has changed is that here we are doing a parallel iterator on accelerations, and otherwise that's pretty much the same. So our change set is very small, and I mean there's a lot in that one line here, now line 65 in this version, but ultimately it is not super long, and our changes are easy to do. We could potentially apply some additional parallelization to any of the other collections we're iterating over when we are, for example, generating our points or computing centers of mass or anything. But if I run the program, it'll take a second to compile, but you can see it's basically instant that our computation has been done to generate the points and to also accordingly do the centers of mass, because of course that gets printed here in main after the initial positions have been created, and therefore there's not a lot of benefit to parallelizing that step. I mean, it might be beneficial, but there's probably not a lot of benefit to doing it because that part of the code is basically instant, so there's very little that we could speed up there. Now, I would be remiss if I didn't show you a little bit of the behind the scenes for how does Rayon actually do what we asked it to do. Now, we covered in the example where we looked at the code, that's how work units are created. We said, look, this is the vector that I have, and I want to iterate over it in a parallel fashion, and that results in dividing up the array, or the collection, and handing out work to somewhere. And now we, of course, can talk about the somewhere. And that is that there are workers to get it done, right? If we just divide up the work without there being some sort of workers to do it, it doesn't really save anything. So the Rayon FAQ fills in some details about how work gets done, and that is that some threads are spawned an equal number of threads as available logical CPUs, so that means hyperthreading cores count. And those threads are the workers. They take work from a queue, and work is balanced using a work stealing technique. That is, if a thread runs out of work to do, it takes work from the queue of another thread. And the technique is nothing new. It's based on some foundational work in this area from something called Silk, and that was developed and the paper was published for it in about 1998. So it's nothing new. It's a fairly standard and common technique for managing how different threads approach work, keeping in mind that a thread might finish its queue faster or slower depending on the nature of the work to be done, and how many workers are available and how much work there is to do. And here's how easy the Rayon change was, and here's a diff between the n-body bins program and the n-body bins parallel. So I used the more complicated version. The diff looks very similar if you compare just the n-body original versus n-body parallel. And yeah, I mean, why does the ease of doing this matter? I mean, as we talked about, it saves on programmer time, but also every change that you introduce has some non-zero probability of introducing bugs, and bugs plural is intentional in that sentence, that a single change could introduce more than one bug. And those things have a cost. To track them down, to figure out how to fix them, all those steps are not free in terms of your time and in terms of money, assuming you are, of course, paid for your work or otherwise doing this in exchange for something. And the more code that you rewrite, the more opportunities for bugs to appear. A minimal change set is easier for a reviewer to review and easier to have confidence that it does what it's supposed to do, right? If you look over this change set, I said, all right, swap the for I in 0 to num points, for accelerations par intermute, enumerate for each. It's a lot simpler to verify that this code is working the way it's supposed to work. And it was super quick to do. I can easily drop this in here and move on to the next thing. So yeah, that moment when your code works, you want that, and you want it more, and you want it sooner. In the words of Queen, I want it all, and I want it now. Now, there are, of course, some warnings about this, and that iterators really do things in parallel, so there is still the possibility of things not happening in the exact same order that they would if they were sequential. In our n-body program, it doesn't matter because at the end, the final state where the vector is completely updated with all accelerations, that happens in the end, regardless of what order the elements were computed in. If threads are taking things and they do some printing to console or writing into a log to tell you about their execution trace, I have processed invoice number 1234 and it is paid, that kind of thing, those would potentially appear in the log out of order because, well, when a thread takes something, there isn't a strong guarantee about what order each work item is going to get done in, because operating system scheduler and stuff like that makes a determination about what threads run when. So that part is really no different than if you were parallelizing it manually with threads, in that there always exists that possibility that things happen in a slightly different order than you would otherwise have expected when comparing, say, the output from a sequential version against the output from a parallel version. You do still have to satisfy the compiler that there are no race conditions, so it is helpful. Automatic parallelization can take some things out of your hands, and you can rely on those implementations being most likely correct, but it isn't a complete solution in the sense that, this prevents any possibility that there is a race condition. What you do in the for each loop still matters. In the previous example, we're okay because we're only operating on our little piece of the slice, and really everything else is read-only, so we're good. But if there were some shared data, keeping track of what is the highest acceleration or anything, we would still have to have some sort of other coordination, atomic types or mutex or something like that, that ensures there is no race condition on that memory. So if you wanted to, for example, find the maximum value in a randomly filled array, this is a good example of somewhere that you would need to use some form of concurrency control alongside using the parallel iterators. For no other reason than, well, we're trying to update a max value, and the max value is shared between all the different threads that are working on the different iterations of it. So let's do it. So we're going to examine here our randomly filled array and try to figure out what is the maximum value in it. So let's look over the whole code. It's really not very big, so it fits conveniently here in one screen. And our main function says initialize a vector, and initialize vectors, we create a new random number generator for a given vector size. We are going to just randomly generate a 64-bit integer, and that's it. Put it in the vector and return the vector at the end. And then we're going to iterate over the vector. And so on that, for each, check if n is greater than the max. Max is assigned n. Okay. Can we do that? Sure. We'll compile it. We'll run it. This one should be significantly faster than anything else. Yes, there are some warnings about unused imports, and we're done. The max value in the array is a really big 64-bit integer number. Okay, that's the original not parallelized program. Let's try to parallelize this. So we want to use the parallel iterator here for our vector. And that on its own, of course, won't work because, well, we have a shared value here for max, and that's not doing what we want. And so what we could do is we could have a mutex, we could have an arc, all of those things. But if you looked already at line 5, you can see the framework of the solution that I have previously written here, which is that I want to make this type atomic instead. So we're going to do atomic I64 here, min. And then we need to do a load ordering sequential consistency, and then store the value n, sequential consistency again, and then load, you know the drill. Okay, let's try that. Yes, of course. We have to load here as well, so I'll just and use that value here. So we load it only once because this is after everything is done, so it doesn't matter. And yes, I can remove mutable here. And we can run our code. Okay, so it finds a max value in the array, and we can run it several times. We might find out it is in fact the max value for an I64, maybe not, depending on run of our program. There's only one very slight, tiny problem with what we wrote here, and you may have spotted it, is that this is not a good use of atomics here, lines 13 and 14, because actually what we did here is we did a read that was atomic, and then the write is atomic, but the two operations themselves are not. And so if you were screaming at your screen and angrily writing in the comments, how could he do this? Doesn't he know any better? You were the chosen one. Don't worry, it's something that I know about and intended to talk about, so we will definitely correct it. But just at a first pass, you'll notice that although you have to satisfy the compiler that there's no race conditions, it's not perfect. It can't see everything that you could possibly do wrong, and this is one of those things. Okay, so what do? Well, actually what we want is a compare and swap operation here. So let's create a variable for this. We'll call it previous value for the sake of this. And if the value we have, we already know is less than or equal to previous value, there's no point in trying to do a compare and swap because we don't want to update the array anyway. And even if our information is a little bit out of date at the time when we are making the decision here on line 14, it doesn't matter because the value that we have is not the biggest. If it was already smaller than our previous max, even if the max has changed in the meantime, it would have only gotten bigger, in which case we're still sure that we don't want to carry on and try to do the compare and exchange because it wouldn't be necessary. We already know the value we have is not the biggest one. So, okay, let's do it. And then we will try to do compare and swap. And our expectation of the current value is the previous value. The new value is n, and ordering is sequential consistency, as we would expect. However, that's not enough, as we know, because we actually could fail, so we want to retry. So while this condition is equal to previous value, then we're just going to spin. We could actually see if we could observe that behavior. Compare and swap was unsuccessful. Right, and the documentation for store a value into the atomic integer for the current value is the same as the first argument, and so actually if the returned value is not the one we were expecting, then we go into the loop. So let's go. You may have noticed that it got stuck. We would see a lot of print line compare and swap was unsuccessful, retrying. Why? We don't update previous value. If we fail to do that and account for what the new thing stored in that variable is, we're going to get it wrong every single time because the value has been changed and our expectation needs to be updated accordingly. So let's do that. We will have to make it mutable, but that's okay. And we will then try again here. Okay, and we got the max value in the array. We can see that compare and swap was unsuccessful some number of times. I suppose if we wanted, we could put a counter on that, and we could say, okay, compare and swap failed this many times. But it appears to be a manageable number. There's a fair number of lines here, but it's not as though this is a ridiculous amount of times. It happens sometimes, but not always, especially when we are trying to update it a fair amount. But let's see how we did. In terms of performance, was this any better? Probably not. We'll discuss that in just a moment. Now, there is a slightly different version of this code in the notes. They really accomplish the same thing. It's just a question of which version you prefer and what print statements you want to have or not have. In any case, our code could be better, but could be worse. I used an atomic type here, and in the notes we use a mutex instead. And here's the mutex version, just to see how simple it is. The generation doesn't really change at all, but this function is a little bit different. We create a mutex, and then we iterate over it. You have to lock it, unwrap, and then perform the modification, and then get the value when we're done. And as we can see, this takes the runtime from 121.6 milliseconds on the parallel version with atomics to about 871.7 milliseconds in the parallel version with the mutex. For comparison, that is dramatically worse than the non-parallel code. It is obvious that this problem really doesn't have enough work to parallelize effectively. The lock-free version speeds it up a small amount, but the mutex version was a little bit easier to write, and it's therefore something you might do, but it makes your code slower. So it's important to consider carefully when you want to apply a library, if you want to apply it at all, because we have to acknowledge the fact that it actually might make things worse if the place that we're applying it doesn't have enough work to do. And that's part of the reason why I don't apply the parallel iterators in the n-body problem to generating the points randomly. It's very fast as it is already, and adding the extra overhead could actually make it worse instead of better.